My name is Eric Voller. I'm the director of this machine shop. This shop's located in the Artificial Intelligence Laboratory. The work that's done in this shop is primarily for the robotics group. There are many students that work and use this shop to support research in robotics. In fact, many of the machines that have been built and are used in research here have been built in this shop. Many others have been brought in for repairs in this shop. I'll take you for a quick tour around the shop, give you an idea of the capabilities we have here. Starting in the back of the shop here, we've got a standard Bridgeport milling machine. This machine's used primarily for working on parts with flat surfaces, rectangles, plates, bars, that sort of thing. Down in the front here, we have a collection of grinders, buffers, polishers, deburring machines. The grinder here is used primarily for working on very hard materials, such as high-speed steel that's used in drills or also used in cutting tools for lathes. The grinder back here is used for more precise work, primarily for sharpening cutting tools and lathes. The machine in the front has a buffing wheel here for producing very fine finishes on metal and plastic, and a deburring wheel on the other side for improving surface finishes on parts typically that have been cut off in a bandsaw. Moving over to this side of the shop, have a drill press, which is used primarily for drilling very accurate holes in parts such as this. Now over here, on the other side of the shop, we have two lathes. Lathes are used typically for making parts like this, cylindrical parts with cylindrical features. Parts such as this, shafting that has steps in it and threads, and also working on discs and rings, such as this. Now right in front of you here is a bandsaw, used for sawing a variety of materials, suitable for plastic, wood, metal. Almost any material can be cut on this saw. Often when you cut something on this saw, there are rough edges left on the part. A common way to deal with those rough edges is with a belt sander like this. This cut has been made on the bandsaw, and the edges of it will be a little bit sharp. Those edges can be smoothed down on a belt sander such as this, or the smaller sander over here. Although the work we do in this lab is very specialized, we focus almost exclusively on robotic work. These machines can be found in almost any prototype shop you'll see around. The courses that we teach here emphasize the qualitative nature of what we do here. So what we focus on is showing real things happening. We show metal being removed with drills, with cutting tools, with saw teeth. The rest of the work, usually involved in teaching students to become competent machinists, that is very much more quantitative, such as speeds, feeds, types of abrasive, coarseness of abrasive, we leave to the students to track down themselves by using a collection of reference books on machine shop practice. The goal of the courses that we teach here and of the video you see will be to give you a qualitative feel for what goes on in the shop. I'm going to be showing you several ways of how to lay out a part. That is, starting with the nominal size of the part, I'm going to show you how to mark locations for the features you want to put in the part, such as grooves, shoulders, slots, and holes. Before I start doing this, I'll always begin with a drawing. It can be just a sketch. The important thing is to have numbers corresponding to every feature you want to make. You'll find you're working in a shop, even when it's fairly quiet, something happens to your brain. You just don't think quite as clearly as you would elsewhere. Especially if a shop is noisy and crowded, so always the possibility of bits of metal, tools, and things flying around. part of your brain is thinking about that and not thinking about adding and subtracting. Do this outside of the shop and you make many fewer mistakes. Come in with this and you're ready to proceed. What I have here is a piece of aluminum. See, it's slightly blue. That's because I've coated it with blue layout fluid. This is a kind of a paint. You spray a coat of this on the surface, and then when you scratch through that surface, you'll very clearly see the places where you scratched. This is a case where more isn't better. You want a very light coat of this on the surface. Putting several coats or one heavy coat leaves a big enough layer so that when you scribe on it, you tend to flake pieces of it off rather than cut a nice line through it. Let's start with some of the simple common tools first. Probably all seen a square like this. You can use this up against one of these finished surfaces along with a scriber. This is just a simple metal tool with a point on the end. To scribe lines parallel or perpendicular to a feature that's already in the part. You can see that line very clearly. That line's only about 0.02 of an inch wide. So if you've been very careful in locating that line, you can, just by eye, machine up to that line and produce a feature that's within 0.02 of an inch of the nominal location. One way to determine the distance from the edge of the part to a scribed line is simply with a ruler. And set the length of the ruler extending beyond the square, line it up against the part, lightly scribe it, line up that scribe mark, and continue the scribe mark all the way across the part. This isn't particularly accurate. Very difficult to accurately set the dimension you want on the square. A far more accurate way to do this is with parallels. These have many uses in the shop. This is just one of them. This particular parallel is 1/4 of an inch thick and 1.5 inches wide. That is a very accurate 1.5 inches. That's 1.500 inches. So if that's the dimension you want, you put this up against the side of the part, and then with another parallel, make sure that both the part and the parallel are in contact with the second parallel. Hold the parts together and scribe the line. Now, these parallels come in increments of 1/16 of an inch. So you can easily build up the dimension that you're looking for by using the right combination of parallels. I've scribed an X here. If I want to drill a hole, for example, at that location, I can mark that with a center punch. This punch has a little taper on the end. Using this with a hammer, align the point with the intersection of the two scribe marks and tap the punch lightly. This gives me a feature to reference from when I drill the hole. Another way of scribing lines that's reasonably accurate is to use a caliper. I can set this caliper to a desired dimension, in this case 1 inch, and holding one of the jaws up against the side of the part, I can use the other jaw as a scriber. This is a very convenient way, very fast way to lay out a part. Disadvantage with this is that because you have to have one of the jaws slightly below the surface, it's difficult to get a very accurate dimension here. I often use this method when I'm going to be milling a part like this using a machine that has digital readouts. I use the readouts to get the location exactly, and I use these scribe marks just for reference to make sure that I haven't made a mistake in reading the drawing. If you don't have digital readouts in the machine and you need to very accurately locate these parts, you can use a magnifying glass to more accurately locate the end of the punch. If you have a need to do a lot of this, you can buy hammers, machinist hammers, that actually have this magnifying glass just built into the handle. That way you don't have to pick up and put down parts while you're making these center punch marks. Here's another handy tool. This is an automatic center punch. It's got an interesting little spring mechanism in it so that when you push on it, you just push down, you can hear that click. Basically hammers the end of the punch into the part. So you don't need a separate hammer to actuate this. We very often want to make circular parts. You can do this with a compass like this. Mark the center of the circle with a center punch. And scribe out the circle. Now, all this is fine if you're making all of your own parts. You've got complete freedom as to where these features go, where you put slots, grooves, bolt holes. But more often than not, you're building parts that are used to fit together existing pieces of hardware, such as this right-angle gearbox. This comes with mounting holes. You no longer have complete control over where you put these features. Several ways of transferring the location of these holes onto this part. A straightforward way, often, is to get the blueprint for this part. Often you'll find enough information in the part catalog as to where these bolt locations are. There's several other ways to deal with this. If the location of this on the plate isn't all that critical, the very quick and easy way of locating these bolt holes. That is with a set of transfer punches. These come in a wide range of sizes. I'll show you a large one here. Basically flat on the end, except for this little point. This point serves the same function as the end of the center punch. We look through here until we find the right size that fits in the hole. If you need to transfer several holes, it's a good idea to clamp the pieces together. It's typically what happens if you don't. You tap this, the parts tend to move relative to one another. I'm not going to clamp it here because putting the clamps on it obscures what I'm doing. Another way of dealing with this problem is to get a punch mark for one hole, set the part aside, go over and drill and tap or whatever you're going to do with that hole, come back, bolt the part down just at one place, bolt it down securely, and then you can punch mark the other two holes, take it apart, and finish those holes as well. That's fine, as long as the holes go all the way through the part. They don't always. I have another gearbox here. The mounting holes are blind. That is, they don't go all the way through. It makes it impossible to use a punch like this. Here's the answer. These are Hyman transfer punches. Now, if we look through here and find the thread size that corresponds to the threads in the mounting holes of the gearbox, in this case 1/4 open this up. What you find inside are these little guys, 1/4 threads, and on the top of them you can again see a little point that serves the same purpose as a center punch. You install these by simply threading them in place. So if you look at the base of the point, there's a little hexagon there. So this works just like a socket wrench. You screw them in until just the point sticks up above the surface. Do that in the other three holes, in this case. Line up your part. And give it a swat. And that transfers quite accurately the location of those 4 blind holes onto your part. Now, so far we've taken care of through holes and of threaded blind holes, and yep, you guessed it, somebody makes the equivalent setup for dealing with unthreaded blind holes. These are used in the same way as the Hyman buttons are used. Another layout technique that we use often in this shop for sheet metal when dimensioning isn't quite as critical is to use a plotter and plot all the dimensions out on pieces of paper, spray them with contact adhesive, and then stick them down to the piece of sheet metal. Now, often for many sheet metal fabrications, the accuracy that you get with this method is more than sufficient, and this is extremely fast, and because you're taking the part you've drawn and transferring it directly to the metal you're going to actually make the part out of, you minimize the opportunity for making mistakes. This machine is a drill press. It actually has a lot in common with a hand drill in that they both have a motor, a transmission, and a drill chuck. The motor of this machine is up in the head here, as is the transmission. If you look down here, you can see a chuck very much like the chuck that's in an ordinary hand drill. The big difference between the hand drill and the drill press is that the drill press is set up with enough structure here so that it can hold the drill chuck and the drills you put in the chuck perpendicular to the parts that you're working on. Unlike where you're working with a hand drill, we often have difficulty aligning the drill so you can drill straight holes. This particular drill press has many features in common with other drill presses. Find up here, there are a couple of levers that are used for changing the speeds in the transmission. There's a lever here for feeding the coil up and down by hand. And there are a couple of controls here for engaging a power feed, which is particularly useful when you're drilling many holes, particularly when they're large, and each hole takes a long time to drill. This is not a very large machine, but there's quite a bit of flexibility built into it. You can see the size of the bed here. It's about 2 feet long. So you can easily put a part on here that's maybe 2 or 3 feet long and a foot or so wide. But with this machine, it's quite possible to work on parts that are much larger than that. And you do that by unlocking the head and rotating it. This allows you to gain access to a much larger area than you would be able to otherwise. It's a very simple arrangement here. This is called a pinch clamp. And pull down on this lever, it relaxes a clamp that is just simply pinching down on this tube. Lift the clamp up, pinches back on the tube, and locks the head securely in place. These clamps are just like the seat post clamp you'll find on a bicycle. The table has a similar pinch clamp arrangement on it. Loosen that. It's possible to move the table out of the way. If you look down here, the base of the machine, there are T-slots here, just like the T-slots that are in the table. And they're also just like the T-slots you'll find in a milling machine. And this arrangement allows you to attach a part to this surface that's perhaps 3 or even 4 feet high and work on it with this machine. This particular machine is equipped with an XY table, much like what you'll see on a milling machine. This is a very convenient add-on to any drill press. This allows you to clamp a part securely in the bed, but that's all you have to worry about is clamping it securely. You don't have to at the same time worry about aligning the part so that you can drill it accurately. You clamp it securely and then make final adjustments to the part in X and Y using these hand wheels. The vise that we have mounted on here is very handy for holding many of the parts that you'll typically be drilling in a machine like this. Typical part you might work on is something that I'll be using for a little bracket. I want to put a couple of holes in here. And lock it in place with the vise. Very convenient vise. Notice there's no hand crank, no screws. This is done with a cam lock. So this lever up, this is free to slide back and forth. Very quick and easy to use. Slide it into place, hold it up against the part, pull this lever down, part securely locked in the vise. Now we're ready to locate these points and drill holes there. Now if you look closely at the part, you can see that I've coated the surface with machinist bluing and scribe lines on it and center punched the two places where I want to drill holes. The next step is to align the spindle of the drill press with a center punch mark. To do that, I'm going to use a center finder. Now, if you look closely, you see that the end of the center finder is free to move relative to the body. This is done, if you look inside, little spring. And the spring pulls the end of the center finder down hard onto the body. We put this tool in the chuck, lock it down tightly, and bring it down until the end of the center finder is in the center punched hole. And you can see here there's a step between the body of the tool and the end of the tool. That's because the hole isn't aligned with the rest of the tool. And to correct for this, turning one of the feed handles to move the entire bed of the machine, the vise and the part, in a direction that will bring things into alignment. I check this occasionally by running my thumb and finger up and down the sides of the tool. I keep making adjustments here until I can't feel the transition from the body of the tool to the end of the tool. And I'll be within about 1/1000th of an inch when I can no longer feel that transition. What's important when you're doing this to not be pulling down too hard on the quill. So if you pull down hard, there'll be enough force between these two parts so they don't want to slide. So when you move the bed, rather than having these two parts slide relative to one another, what happens is the quill deflects slightly. I'll show you what this looks like. I'll pull down much harder than I should, move the bed a little bit off to this side, and now reduce the force. See the step that's produced there? That's probably 10 or 15 thousandths of an inch, which may be beyond the tolerance that these parts can be made to work. So, be careful to apply just enough force to maintain contact. Bring everything into alignment. Okay, we're all set. Now I'm ready to start drilling the hole. I'll start drilling the hole with a center drill. This is a very special drill. It's very short, and most of the drill has no flute, so it's very stiff. A regular drill is long enough and flexible enough so it tends to wander around a little bit before it starts to cut. The center drill is stiff enough so that it won't deflect significantly, and we'll get an accurate start to the hole. Now if you look closely at the hole that I've just drilled, you can see that I've drilled down to a depth about like so. What I've done is to make sure that I've drilled deep enough so that I'm up on the tapered part of the center drill. What that does is act sort of like a funnel, so that when you start drilling with a regular drill, the drill is funneled down into the very accurate start of the hole produced with the center drill. And there's the finished hole. Now, the top surface of a hole like this is usually relatively clean. But typically on the other side, where you've broken through, there'll be kind of a jagged edge. It's a good idea to remove those burrs. Now, there's several tools that can be used for that purpose. It's a very handy tool for deburring. Simply put it in the hole, apply a little bit of force, and turn it around a few times. And that puts a nice clean chamfer on the hole. The same tool can also be used for cleaning up the edges of parts, like this. Other common deburring tools look a little different but serve the same purpose. This tool, push it into the hole and give it a couple of turns. Again, you can see nice clean chamfer that's left behind. You can also do this with a deburring tool that's meant to be used in the drill press. Lock this tool in place. And just touch it down. This will also nicely deburr the hole. I've now completed the second hole. For many parts, we're now done. With these holes here, we can now run bolts through them and attach this part to other parts. But often, you'll want to thread these holes so that you can thread fasteners into them. And that's done with a tap. Tap looks like this. You can see the threads on it. If you look at the end, the tap, the last few threads are only partial threads. This tap is ground on a taper. And that's so, as you're turning this into the hole, the tap only removes a small amount of material at a time. The material that's removed then sits down in these grooves in the tap. You're tapping by hand. Generally hold the tap handle like this. Now it's possible to tap a hole by hand like this, holding both the tap and the part. Now the tap's all the way through the part. The problem with this, especially when the parts are thin, is just like the problem you have when you're trying to drill a hole with a hand drill. Very often, the tapped hole will not end up being perpendicular to the part. The drill press comes in handy for tapping holes and avoiding this sort of problem, because you can use the spindle of the drill press to guide the tap. We'll lock the part back in the vise, and again, using the center finder, we'll relocate the hole that we drilled. you look at the back of the tap handle, you find that most of these handles will have a hole in them. It's not just a hole drilled in straight. You can see a little taper on the edge of the hole. That's so you can use a tool like this to guide the tap handle. You lock the guide into the chuck. Put the tap handle in place. Now we know that this whole assembly is very perpendicular to the surface. Applying a slight amount of pressure with the hand feed maintains contact between the guide and the tap handle. Be very careful here that you do maintain some pressure. If you don't, it's quite possible you're tapping the hole for it to slip out and break the tap. Now you can see that this hole has been tapped much more perpendicular to the surface than the previous hole. I tapped both of these holes dry. That is, I didn't use any cutting fluid when I was doing the tapping. In many materials, it's a good idea to use a few drops of cutting fluid, in particular for materials such as the softer alloys of aluminum or steel. It's very important to use a little bit of cutting fluid. Again, I try to minimize my use of cutting fluids because of their toxicity. You'll find with many materials, such as most plastics like nylon, Delrin, that sort of thing, they machine and thread and tap quite well dry.